we will continue our discussion on the nuclear force today. So, let us recap what we did in the last lecture. We discussed the deuteron, specifically its magnetic dipole moment and the electric quadrupole moment, and we saw that the magnetic dipole moment of the deuteron arises due to the nuclear the spins of the nucleons and also due to the orbital angular momentum of the nucleons inside the deuteron. And experimentally it is found that orbital angular momentum L equal to 0 state is predominant in deuteron, or deuteron is predominantly in L equal to 0 state. About 96% of the time it is in that state, and 4% it is in the L equal to 2 state. And the quadrupole moment, that is electric quadrupole moment, is measured to be 0.00288 E barn. The barn is 10 power minus 24 centimeter square, just to remind you. All right. So, today we will discuss the nucleon scattering. We are basically interested in trying to understand the nuclear forces, looking at different systems, nuclear systems and the processes. So, deuteron, which is one of the simplest bound states of the nucleon, two nucleons bound state, a neutron and a proton, and a study of the properties of this deuteron will give a lot of information about the nuclear force. But that will not be enough. For example, we saw that in deuteron, neutron and proton are in a parallel spin state, and we do not have any bound state with antiparallel or spins aligned antiparallel to each other, for example. And if we want to study the nuclear force, spin dependence of the nuclear force, okay, with antiparallel spins, details about that, etc., we need to actually go into different systems. Since we do not have any other two nucleon bound states, we rely on something else, some other process, which is basically scattering of the nucleon on nucleon. So, we will bring this one nucleon near the other one, another one, say a proton is brought near a neutron. You can have actually a proton static also, like you can have hydrogen gas in as a target, and neutrons with some kinetic energy can be sent to this target, and then study the system, study what happens, what is the behavior of the neutrons when they encounter the protons. So, such scattering studies reveal a lot about the proton neutron and proton and neutron interactions and their forces, the strong nuclear force between them. So, let us look at some simple basic ideas of the nucleon scattering. Here N stands for either proton or neutron. So, for low energy systems, if we are having a small kinetic energy compared to the mass of this, say for example, a few MeV, up to a few MeV kinetic energies, because the mass of the neutron is about 1000 MeV, a few MeV can be considered as a non-relativistic region. So, in such cases, what will dictate the equation, the scattering process is the Schrodinger equation basically. So, the Schrodinger equation in spherical polar coordinates is what we have written down here. So, it has the psi, which is basically the wave function that represents the particle in the nucleon, and it is in principle in general a function of all the three spherical polar coordinates r, theta and phi. Okay. And there is a potential V, which is basically the nuclear potential that will cause the scattering to happen or cause the interaction to happen. Scattering is basically like you have a proton somewhere and say for example, a neutron comes near that and then scatters off to some directions, and this is the basically the neutron proton for example. And when the neutron comes near the proton, it sees the nuclear potential, which we denote by V. And to understand the nuclear scattering, we need to actually have some model potential. So, we will take a simple model potential, which is basically a square well potential, a 3-dimensional square well potential, which is actually spherically symmetric. So, we will consider the potential V r to be some value V negative V 0 for small r up to some radius r 0, and beyond which it is equal to 0. So, with this potential we will actually consider the equation, Schrodinger equation, and then again we will separate the variables by defining psi, the wave function, as a product of 3 functions which are of functions of variables r, theta and phi separately, and only functions r is a function, capital R is a function only of the variable r, theta is a function of the variable theta, phi is a function of the azimuthal angle phi. Okay. And time similarly is separated from the spatial part of this one, and from the equation easily it is seen that the form of the time dependence is exponential minus I e over h cross time t. And now, the radial part of the wave function is we will rewrite as u over r, another function u, and this u will now satisfy the equation minus h cross over 2 m d square u over d r square plus v plus L into L plus 1 h cross square over 2 m r square u e u, where so this is the equation, Schrodinger equation satisfied by the radial part wave function. Here L is the angular momentum quantum number, and let us say we want to concentrate on a particular L value. And so, we will stick to L equal to 0 case, and in that case solutions, we will look at the solutions. See, looking at the equation, Schrodinger equation, we have V non-zero up to r is equal to r 0. So, for that part we will consider again energy to be larger than, or energy to be positive, because here we are talking about the scattering of electron, or sorry, a scattering of neutron over a proton, and in that case electron, so the neutron, incoming neutron has kinetic energy, and we will assume that the total energy is larger than the potential, and so it is positive there. This gives us the solutions of the equation as u 1 equal to some constant a times sine of k 1 r plus some another constant b cos k 1 r for the region r smaller than r 0, and a very similar thing for r larger than r 0, but now we have another wave vector k 2, and the coefficients C 2 and B 2 can be different, or in general different from A and B respectively. Okay. So, k 1 and k 2 are given in terms of E and V 0. So, for region r less than r 0, we have the potential non-zero, and we have an expression for the wave vector in this fashion, which is equal to under root 2 m E plus V 0 over h cross square, and k 2 we do not have any potential, the potential is 0 in that region, and therefore, we have this to be 2 m E over h cross square under root. For the wave function to be finite as r goes to 0. Okay. So, we have the potential, let me draw the potential again. So, we have the potential starting from 0, some non-zero potential minus V 0, and it is equal to 0 from r equal to r 0 onwards. And we want for the region 1 where u 1 is the solution, r tending to infinity, we have to include the point r equal to 0 as well. So, as r tends to 0, if we want the solution to be a finite solution, we need to keep b equal to 0. Why? Because the wave function psi r, now if we are actually considering L equal to 0 solution, then the angular part will only give some kind of a overall constant, we will neglect that for the time being. So, the total wave function is essentially r apart from the time dependent part, which is again trivial and we will not write it here, and this in terms of u is u over r, and this then because of u 1 it is for the region of interest near r equal to 0, it is a sin k 1 r over r plus b cos k 1 r over r. So, we know the limit of going to 0 sin k r over r is equal to sin k 1 r by r is equal to k 1, which is finite, no problem. But if we take limit the second term, limit r going to 0 of cos k 1 r over r, this is going to be infinite. So, if we want the wave function to behave properly as r goes to 0, then we cannot take the second part or b cos k 1 r as a solution, as part of the solution. So, we will have to take b equal to 0. So, we will consider that, and there are other the other boundary is r equal to 0, sorry r equal to r 0, where the potential actually drops down to 0. Okay. So, here we have the boundary condition u 1 r 0 equal to u 2 r 0, that is the boundary, that is one of the boundary conditions. The other boundary condition is the derivative of u 1 with respect to r at r equal to 0 is equal to the derivative of u 2 at r equal to 0. So, they should be equal. So, these are the two boundary conditions, and then this gives us one C 2 sin k 2 r 0 plus d 2 cos k 2 r 0 equal to, now we have only one term which is a sin k 1 r 0. So, there, and this is from equating u 1 and u 2 at r equal to 0, and when we take the derivative, that will bring out k 2 here, and then you have C 2, sin will give you cos after differentiating. So, cos k 2 r 0 plus minus k 2 d 2 sin k 2 r 0, and this should be equal to k 1 a cos k 1 r 0. So, these are the two boundary conditions. Now, let us redefine to make it in a slightly nicer form. We redefine C 2 equal to C some constant cos delta and d 2 equal to C times sin delta, some delta 0, let me take it as delta 0. So, this will give the boundary conditions to be C sin k 2 r 0 plus delta 0 equal to a sin k 1 r 0, okay, and k 2 C cos k 2 r 0 plus delta 0 equal to k 1 a cos k 1 r 0. This will give, if you divide one by the other, that the second one by the first one, then that will give you k 2 cos by sin is cot. So, cot k2 r 0 plus delta 0 equal to k 1 cot k 1 r 0. Okay. So, in principle we can find out this delta 0 from known k 1 and k 2. K 1 and k 2 are given in terms of E and V 0, and suppose we know also the range of the potential R 0 from other data or other experiments or other computations, and then in principle we can invert this to get delta 0. Now, let us look at it a little more detail. Like we had the incident wave function psi in as A sin k r exponential minus I omega t. Omega is the frequency which is E over h cross. Okay. So, if we consider some potential scattering, some particle scattering over or a wave function, quantum mechanical wave function scattering by a potential at the scattering center, then we can in principle think about analyze the scattering in this fashion. We have incoming wave, which let us write down as A sin k r e power minus I omega t, where now r is the radial distance from the scattering center. So, this actually I can write down as A over 2 I k sin k r, I will write in terms of the exponential as I k r minus e power plus minus I k r over 2 I into e power I omega t, A over r, this over r. We had a u with A sin k r, and in the spherical part of that the wave function we have u by r, which is A by r sin k r e power minus I omega t, and then that can be rewritten in terms of exponentials as A over 2 I k e power I k r over r minus e power minus I k r over r. Now, you can ask the question, what happens when a particle comes or wave function like this comes and encounters this scattering center. Okay. So, here actually in this way of writing this plane wave, this has two parts, one e power I k r over r, which is actually called a spherical wave, which is in this case no, in general it is actually an incoming, it corresponds to the incoming spherical wave, and minus I k r is the incoming one, e power I k r over r is the outgoing spherical wave. We will not go into how exactly we arrive at this conclusion, but essentially we will have to look at the e power I omega t, the evolution of this, and then we will see that for from physical arguments we can come to the conclusion that e power minus I k r over r corresponds to the incoming wave, incoming meaning coming towards the sender, okay, and e power I k r corresponds to outgoing, it is going towards the away from the scattering center. So, two spherical waves. And general scattering theory argument will say that well, when the scattering happens and when we look at what is the resultant wave after the scattering, then we have some psi r which is very similar to the incident wave, but with a slightly changed outgoing spherical wave. Okay. The incoming spherical wave part remains the same, and the outgoing spherical wave actually picks up a phase beta, we denote that by beta here. Right. So, this is the only thing that happens when we have scattering of a quantum mechanical wave function like this. For then this particular thing from this angle, when we look at the wave function that we had written down, which we had obtained using the square well potential and the scattering of the square well potential on the scattering of the square well potential, we had written down this as C over R sin k to R plus delta 0. Okay. This is essentially equal to, or you can write now this one as e power I k to R plus delta 0 divided by R. So, R I am taking inside. So, it is C minus e power minus I k to R plus delta 0 divided by R by 2 I, of course, and the time dependence is also taken away. There is exponential minus I omega t, which is always there. We are just not writing that here. Now, this can again be written as C over 2 I e power I k to R plus 2 delta 0 over R minus e power minus I k to R over R. Okay. But what is left out is exponential minus I delta 0. So, I have taken exponential minus I delta 0 out of this two terms, and now this is in the form like this. Compare this with psi equal to C over, sorry, earlier we had written it as A over 2 I k, okay, e power minus I k R plus beta plus I k to A minus divided by R e power minus I k R over. Now, this tells us that we have, if we identify beta equal to 2 delta 0 and C or A as k C e power minus I delta 0, then we have the earlier expression in the same form as the general expression. And now, once you have the wave function psi like this, okay, psi in this fashion. So, we have let us say, let me write it again, psi incident is equal to A over 2 I k e power I k R over R minus e power minus I k R over R. Okay. And after scattering, we have A over 2 I k e power A over 2 I k e power minus I delta 0 e power I k R plus beta minus e power minus I k R over R. And if I now consider the scattered wave function as psi minus, take away the incident wave function from this, that will amount to be A over 2 I k, okay, e power 2 I, should have written it I 2 delta 0 minus 1 e power I k R over R. And now there is we can write down the probability current corresponding to these two psi j, the psi in and psi out, and I will leave it as an exercise which I will spell out explicitly at the end of the lecture. So, you can work it out, it corresponds to this h cross over 2 m I psi star dou by dou r psi minus dou psi star dou r psi, and for the psi in, this is equal to h cross over m k r square mod a square, and corresponding to the scattering or scattered wave function, it is h cross over m k r square a square sin square delta 0. Okay. So, this sin square delta square part is basically the difference between the initial incoming current and the outgoing or the scattered current. Now, what does this mean actually? How do we actually physically understand this? So, okay, in the scattering, we have let us say we want to understand this more in terms of some physical quantities. So, let us say what is happening, let us consider some kind of a classical hardball scattering. Okay. So, if we have a beam of incident particle and then encountering some kind of a hard ball, part of it hits this surface of the ball and then some of it will go into a scattered into some region, and something else, other things will scatter into other regions. So, let us focus on some particular region. Say, let us consider some small area of cross section denoted by d sigma. So, if J incident is the incoming current, that is the flux of the particle coming in, number of particles crossing unit cross section in unit time. So, this if I multiply by some cross section d sigma, that will give me the number of particles crossing that area in unit time. So, this many number of particles, let us say, scatters off into the region here, okay, into a solid angle d omega. I presume that you are all familiar with what is mean by solid angle. So, the area corresponding to d omega is, if it is r distance away from the scattering center or the scattering the ball, then area corresponding to this is r square d omega. So, if J scattered is the number of the scattered, the current or the flux of the particle which is scattered into the scattering solid angle d omega, then the number of particle in the area r square d omega will be J S C. So, suppose we assume that the particle which are crossing d sigma cross section scatters into solid angle d omega at some angle theta and phi. In that case, so this is not a good way of writing it. So, let me do that again. So, this is the distance r, this is at an angle theta, and I do not want to complicate the diagram by writing also the azimuthal angle, but there is that azimuthal angle as well involved there. Now, we can define or rewrite this if we know J S C and J in, okay, and if we know what is the solid angle the detector for example covers, then we can get the d sigma from here, or looking we can from an experiment, from a scattering experiment like this, we will be able to say for a detector of d omega solid angle kept at a distance r from the scattering center, if J C is the current or the flux of the particle that it receives, okay, and J n is the incident flux, then those particles would have gone through this d sigma cross section, right. So, this is the kind of physical interpretation that we can give from here, considering or comparing the two currents. And in quantum mechanics, we can actually define again d sigma as J c of the probability current, and J in is the probability of the incident particle times r square d omega as the cross section or differential cross section. And for a particular particle or a wave function corresponding to a particular particle, this will be interpreted as the probability for a particle to scatter into solid angle d omega when it encounters a potential which we have considered. All right. So, this is the interpretation that we will give here. And now, in our case, we have d sigma equal to J c is known, J in is known. Therefore, putting it together, we have say J s c over J in r square d omega corresponds to some or equal to sin square delta 0 over k square. And if we want the total probability of scattering, we have to integrate d sigma over d omega. All right, this is basically d omega as well here into d omega. So, that is essentially equal to integral sin square delta 0 over k square d omega, since this quantity integrand does not depend on theta or phi. We have 4 pi over k square sin square delta 0 as our total cross section. Remember, we have considered L equal to 0 case, which is actually a spherically symmetric situation. So, that is why we have this result. If we take some other L value, then we will not get such spherically symmetric situation, and we will have d sigma over d omega as a depending as a function of theta and phi in general. All right, that we have some idea of what is the scattering, a nuclear Nucleon scattering in particular. Let us consider specific cases by putting in some values. Let us take situation with energy something around 10 keV, which is very small compared to the nucleon mass, and we know from from studies of the deuteron state, we come to a number 35 MeV for V 0. So, this is from deuteron bound states. Okay. Now, we can put this back in our expression, and then let us say we can extract the delta 0 from the earlier expression that we had written down, and we can put that back in this cross section, and it corresponds to something like 4.5 or 4.6 into 10 power minus 24 centimeter square, or equal to 4.6 barn. But experimentally, proton neutron scattering cross section is given to be something like 20 barn for low E values. So, low energy scattering values experimentally gives sigma is equal to about 20. So, what is happening? To understand this, what we do, we have to consider the spin dependence of the nuclear force. So, we have the spin states when the nucleon, say the neutron, comes near the proton, the total spin of the system depends on the combination, the angular momentum combination of the nuclear, the spin of the neutron and the spin of the proton, and both of these sp and sn are half spin particles, and therefore, total spin s can be either 1 or 0, right. So, we have either a triplet combination or a singlet combination. Singlet 0, spin 0 is called singlet because that has only one projection allowed, 0, and triplet has 3 projections plus minus 1 and 0 allowed. So, it has 3 different z states possible, that is why it is called a triplet. Now, such cases, supposing we have the total sigma depending on the triplets and singlet, let me denote it by sigma t and sigma s respectively. And since triplet has 3 states and singlet has 1 state, okay, we have to also have a multiplicative factor of 3 over 4, an averaging factor there, and 1 over 4 here to find the total cross section. Now, what about the value that we computed? Remember, when we computed this, we used actually the information from obtained from the deuterium bound states, and deuterium is deuteron is S is equal to 1 state. So, this gives what we computed is actually sigma t, which is equal to about 4.6 barn. Now, we know experimentally sigma is equal to 20, say let us to be more accurate, 20.4 barn, and these two values put together will also tell us that sigma s is about 67.8 barn. So, we can somewhat understand what is the discrepancy, why is this discrepancy coming, and then there can be other nucleon scattering processes which can actually verify this. Indeed, we will not go into the details of all these things, but lot of experiments are consistent with the understanding and that we have from such elementary studies. And you should also remember that when we solve the scattering problem using the potential, which is we used a potential which is very crude approximation of the nuclear potential, actual nuclear potential. So, there will be corrections to that, and considering all those aspects, we can actually try to understand the nuclear force in a better way. Now, before we conclude, let me just suggest some of the questions, some of the things that you can work out, exercises that you can work out. Okay. One thing is, I would urge everybody to go through the quantum mechanics, take your favorite quantum mechanics textbook and then go through the scattering theory section on scattering theory. So, quantum mechanics scattering problem, right. So, almost all the books will be dealing with this, some in detail, more detailed than the other. So, you take the book that you think is best and read through that and understand the cross section clearly. A scattering problem, how to analyze a scattering process. Okay. So, that will give a better understanding of today's discussion. And another thing that we did not really work out in detail is the current that we considered. So, work out, obtain J in equal to h cross k over m, absolute value of a square, and J S C is equal to h cross a square over m k r square, sin square delta 0 for problem discussed today. So, this is easy to work out, but I am leaving it to you to do that. All right, with that we will conclude today's session.